Hello class, today I'm going to teach you some details about random vibration. You know about the harmonic vibration, and when we using harmonic vibration we need to have a assumption that loads applied to our part, they're harmonic, and this is a huge assumption. Sometimes it's not possible to have a harmonic assumption, or having a harmonic assumption creates a lot of inaccuracy in our data, so we may need to have random vibration analysis. Basically, we are going to consider vibration as a random, and the statistical analysis is going to be mainly applied to this to the loads we are going to have. So we should expect some statistical terms in this type of analysis. Let's start with again static structure analysis. I already draw some like random geometry. I will show you. Let me first import it and then later show you what it's about. And I just named it random. So this geometry is going to be something like a mobile holder inside a car. It has one part attached to some part of a car, and the other part is going to have your phone, yeah, something like that. Let's see the geometry and then continue with the analysis. Okay, it's here. Okay, it's something like this. This circular part is going to be our fixed support, and the end is going to have some type of weight because of the some type of load because of the mobile. Yeah, it's just simple geometry to investigate this random vibration analysis. At the beginning, we are going to investigate static behavior, and then add model analysis, and finally random vibration. Let's wait for the Ansys to open the model. Okay, we have the model here. Let's mesh it. I'm going to let's go with 6mm. If it wasn't enough, we can refine it a bit more. Okay, good enough. And for the analysis, let's have fixed support here. For the vibration analysis, you can have fixed support, you can have displacement, and one more, I think remote displacement, something like that. So it is going to support just three different supports. What else? I need to add some type of pressure because of the object we have here. Let's go 0.3 megapascal, and let's add acceleration, why not? Where is it? So I add G here. Okay, the direction is correct. So it's millimeter per second square, so it's going to be 9810. So this is our G for the solution, total deformation, and something one misses. Stress, let's solve it. So this is our basic analysis. Okay, now you can see about 3 millimeter deflection we have at the end, which we put our load here, and stress is 200 megapascal. Okay, so now let's go and find natural frequencies. So I'm going to drag modal analysis here and go back and extract their natural frequencies as modes, because they're very important for us. Those are the frequencies we usually need to avoid and consider in our design. Okay, now we have modal analysis. Again, we just need to include our acceleration, fixed support, and solve it. Okay, we have 6 natural frequencies here. By the way, if you select this analysis setting, you can define how many frequencies you want to extract. You can go 10, 20, depends on the accuracy you're looking for. Or you can have a range. Sometimes you say, I have already designed everything about this holder, and I know the frequency range. It's about, for example, 1000 to 2000. I don't want to waste computation, so you put the range here and say, okay, I want to have from 1000 to 2000. I don't care about the other ranges. Anyway, so for now we extracted 6 frequencies. Okay, extract the data again. Okay, these are our natural frequencies, 127 to 2571. We need to know the modes. Okay, let's see which one is related to our loading. So the first one is related. This is side to side. These are the torsions. Okay, different modes. Okay, I'm interested mainly on the first one because our load is there, and when car is moving, we expect to have uh, this type of vibration. Okay, so let's start with random vibration analysis. Where is random? Here. This time I need to have results of modal analysis. So I'm going to drag it to the solution to have the modal analysis data in our results. If you drag it to the model, you should manually solve the modal analysis inside the random vibration to have those data. So why not dragging to the solution? Okay, as you can see, the first one is modal data. If you drag to the model, not to the solution, you're going to have nothing here or empty this part. You should manually select the modal analysis to transfer data there. Okay, now for the random vibration, you need to specify what type of vibration we have. The type of data we can have very complicated vibration data from the tests or some handbooks, some type of data, or simplified cases, which we call it PSD. Let me show you what is PSD. PSD is power spectral density, and as you can see in this page, it is mean square values analyzed, and it's spectral because it's about frequency, and the density because it's a normalized data, and the unit for the data is going to be g power 2 divided by frequency hertz. G is meter per square second square. So we need this type of data to put inside our random analysis. Okay, I already generated those data here. As you can see here, this is our acceleration. It can be G acceleration, it can be just acceleration, or let me show you all the possibilities here. Right click on random vibration, insert PSD for acceleration, PSD for velocity, PSD for G acceleration, PSD for displacement. Depends on what type of data you have for this random acceleration, you can select any of these. If your data, like me, is PSD G acceleration, I'm going to select that one, and select fixed support. If you had several fixed support, you select all fixed support. Okay, I selected fixed support, and I'm going to put the data here. Let me copy paste. Hopefully the copy paste is going to work. Yeah. Now I have all the G acceleration data regarding this equipment. This is data I found online for the random vibration inside what was the racing cars. So which direction? It is for X direction, which is the vertical one. So let's select X. So what solutions I want? As you can see, we have limited solutions here. It's not like as many as statistical analysis. The reason for this is, again, it's about statistics, and the results are limited here, but later, if you need any type of other results which is not provided here, you may be able to post-process later. So let's go directional results. I'm looking for directional results. Directional deformation in x direction and sigma 1. Now the statistical terms coming. Sigma 1, remember normal distribution? Let me Google it. Okay, this is normal distribution. 1 sigma is going to be here, 2 sigma a bit bigger, includes larger area, 3 sigma much bigger. So basically here says, give me the deformation in x direction with the possibility of 1 sigma, which is 68.269%. If you want higher, you can go 2 sigmas, 3 sigmas. So I can say, okay, in x direction 1 sigma. I need more data. Let me show you directional again. This time x direction 2 sigmas, just to show you what is the difference, and directional in x direction 3 sigmas. So 3 sigmas is 99.73% is the possibility of having total directional deformation in x direction shown here. What else I'm looking for? I can have something about stress. Why not? Let's go stress. One misses. Stress again. 6. I can again repeat for different sigma. This is 2 sigma, higher possibilities, and 3 sigmas. So the one misses stress in this case, the possibility of happening that is 99.73%. What else? I can even include solution, fatigue analysis, and say what is the life or what type of damage we are going to have for the life and damage. Okay, let me solve this part and then check the results. Okay, for the fatigue, it says in output control, I need to make the velocity and acceleration yes. Output controls, velocity yes, acceleration yes, to be able to calculate fatigue. Okay, now I have all the data. So with 68% possibility, we are going to have this type of deformation in x direction. The value is very small here. If I increase to 2 sigma, it's getting bigger, 3 sigma even bigger, because the possibility increases. So this range getting larger to include all the possibilities. How about stress? Small, gradually getting larger because of the g acceleration we put here. So these are the 3 different one misses stress for sigma 1, sigma 2, and sigma 3. How about life? We can see this is the minimum life, 2.9 times 10 power 5 seconds. We can calculate how many days or how many weeks is that. And let's see where is the damage. Okay, we are going to have a damage mainly in this area, and I need to make sure this area is a little bit stronger, maybe add a more meat here and make it a little bit thicker. And of course I need to improve the mesh quality to have a better data, but probably the weakest area for this mobile holder would be this area, which we need to investigate. So as you can see, first we did the model analysis. First just general static analysis, and then model analysis to get the natural frequencies and modes, then random vibration. But remember, for random vibration you need to have some data from calculations, from experiment, to see what type of random vibrations we have. I imported those vibration random as a PSD table, and then we extracted the data, the type of deformation in any direction, or stress, or life, or damage, or anything else. Okay, thank you very much, and see you next time.